All right, so we're going to pick up where we left off last lecture with talking about valence electrons. So valence electrons are, remember, those that are in the outermost shell. They're the ones that are held the most loosely, in around the nucleus. Because if you remember, the shell that's closest to the nucleus has the lowest energy, it's the most stable. So as you go out, further and further from the nucleus, you get higher energy, and those electrons are the most unstable. So they're held most loosely and are the most easily lost or shared. These are the ones that are involved in chemical bonding. And except for helium, the number of valence electrons for any main group element, remember, not the transition metals, it doesn't work for these guys, but all of the main group elements, meaning the ones that have the A number, the A behind their number, is the number of valence electrons. So group 1A has 1 valence electron, group 3A has 3 valence electrons, group 7A has 7 valence electrons. And we had also mentioned that, remember, the row number, like this is row 1, 2, 3, etc., is the number of shells for those electrons. So this guy down here, francium, would have 7 shells full of electrons, and his last electron, his valence shell, the 7th shell, will only have 1 valence electron in it. Okay, because he's in group 1A. So that's a little intro for valence electrons. Let's take a look a little deeper. All right, so the chemical properties of all the elements are basically determined by the number of valence electrons they have. So remember, it's a group, so everybody in a whole group or family of elements on the row of the periodic table, or in a group of the periodic table, have the same number of valence electrons. So if they have the same number of valence electrons, they're going to have the same chemical properties as well. So they're going to be bonding with the same ratios. They're going to be making the same kind of compounds. Now, elements with 8 valence electrons, those are the noble gases, the helium group here. Those are the noble gases. They have 8 valence electrons, and that is particularly low in energy and very, very stable. So basically, all other elements want to either gain electrons so that they have the same amount of valence electrons as those noble gases, or they want to lose their valence electrons so that they have, that underneath shell of a full valence shell as well. So let's take a look and see how that works. All right, so those elements with electron configurations super close to the noble gases are the most reactive because they contain noble gas configuration by either losing or gaining a small amount of electrons. So we're talking here the halogens, right, and also the alkali metals. Both of those are very, very close to the noble gases. The halogens here are just 1 away, so they just need to gain 1 electron to be like those noble gases. And the alkali metals have just 1 extra electron than those noble gases, so they just need to lose an electron in order to have the same number of valence electrons as the noble gas near them. Okay, so same thing, with the alkali earth metals. That is group 2 right here. They are pretty close as well because they only need to lose 2 valence electrons in order to be like the nearest noble gas. And the oxygen group is 2, he needs to gain 2 more, so he'll have a negative 2 charge in order to be like those noble gases. So in order for elements to bond, they need to either lose or gain electrons in order to be like the noble gas nearest them. All right, so since we're talking about the periodic table and looking at some of the organization that the periodic table tells us, like electron configurations and number of valence electrons and whatnot, let's take a look at some of the periodic trends that occur as well. So atomic size is the first one we're going to take a look at. Atomic size is defined as the distance between the outermost electron and the nucleus. So if you take a look going across a period, number of protons increases, right? So if the number of protons increases, that results in a greater pull on the electrons from the nucleus. So if there's more pull on the nucleus, and remember, because the nucleus would pull on electrons because it's positively charged, right? And there's the protons in the nucleus are positively charged, and so they're going to be attracted to the electrons that are around them, right? So if we've got more protons in the nucleus, it's going to result in a greater pull on those electrons from the nucleus, causing the atomic size to decrease. So the atomic size, as you go across a row, is going to decrease, okay? Because remember, they have all of these guys have the same amount of shells. So like if we're looking at this one, they all are going to have 2 shells, okay? But fluorine and helium are going to have many more protons than lithium does. And so those 9 and 10 protons in fluorine and neon are going to pull on the electrons more, and they're going to hug them closer basically to the nucleus. So the size is going to be smaller. Now going down a column, okay, the size, remember, as you go down, the number of shells increases, right? And so if the number of shells increases, then you've got electrons that are further and further away from the nucleus, right? And so those, protons, however many protons they have, aren't going to be able to pull as hard. And that's going to cause the atomic size to increase. So as you go down a group, atomic size increases. Okay, so that's basically kind of the logical scientific explanations of why it decreases going across and increases going down. All right, so choose the larger atom in each pair. So if we know that, remember, as you go across, size decreases. As you go down, atomic radius or size increases. So if we're looking at carbon versus oxygen, which one is larger? It's going to be carbon, right? Because as you go across, it's going to get smaller. So oxygen will be smaller than carbon. Now, if we're taking a look at lithium versus potassium, again, as you go down the group, okay, it gets bigger and bigger. The size increases. So potassium is going to be the larger atom between those two. Next example is carbon versus aluminum. Okay, well, let's think about this. As you go across a group, you're going to decrease. So carbon is one further to the right than aluminum, and so that's going to be smaller anyways. Okay, and then aluminum is one down, which means he's going to be bigger than carbon as well. So in this one, aluminum is going to be bigger than carbon because aluminum is one row down from carbon, right? So that increases its size right there. And then carbon is one more group to the right of aluminum, so that decreases carbon's size. So either way you slice it, you're going to have aluminum be a bigger element. Now, last but not least is selenium versus iodine. Selenium versus iodine. Okay, so which one's going to be bigger? This one is kind of a toss-up because remember, as you go across, size decreases. So, if these guys were on the same level, iodine right here would be smaller than selenium because he's further over. However, he is one down, so that means he might be bigger. So this one's a toss-up. Those ones you can't really tell unless you're given data. So those ones you won't see on, those kinds of examples you won't see on tests or quizzes. It'll be very clear-cut ones like we did up here, 1 through 3. All right, so the next periodic table trend is ionization energy. And ionization energy is exactly what the name means. Ion, right, is a positive or negative charge, atom. And energy is energy. So ionization is the energy required to remove an electron from an atom, right, so that they will have a positive charge. So ionization energy is the energy needed to make an atom an ion. There we go. So, for example, sodium plus adding some energy, okay, is going to basically pop off one of his valence electron, and so sodium's now going to have a positive charge, and you're going to have an electron kind of floating there, being transferred, basically. So ionization energy is the energy required to remove an electron from an atom. Now let's compare sodium and chlorine. So we have sodium, and we've got chlorine over here on the other side. All right, so since removing one electron from sodium would give it its noble gas configuration, right? So if you lose one, then he'd be just like neon over here. He's good with that. He likes that. He wants to do that. All right, so if he loses an electron, it would be super easy for him to do that. So we say that he has low ionization energy. Doesn't need much energy to lose that electron because, hey, he wants to lose that electron so that he can have the same number of valence electrons as neon, right? But if you take a look at chlorine on the other side, okay, if he loses an electron, now he becomes like sulfur, all right, instead of argon right next to him. So removing an electron from chlorine would not give it a noble gas configuration. All right, so that means he doesn't even want to lose electrons very easily. So what that means is that it's going to take a heck of a lot of energy to get that electron away from chlorine, because what does he want to do instead? He wants to gain electrons. So he's going to hold his electrons super, 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 super tightly because he doesn't want to give any away. He wants to actually get more. So we can say that chlorine is going to have lots or high ionization energy. So here's the general trend. As you move across a period from left to right, okay, ionization energy increases, right? Because as you get closer and closer to those noble gases, it's going to require more and more energy to take away electrons. Because remember, these guys over here are going to want to gain electrons to become like the noble gases. Now, as you go down a group, okay, the ionization energy decreases. And let's take a look why right here. So as you move down a group, electrons in the outer shell are going farther and farther from the positive nucleus, right? So that means, remember, as you go down a group, you're getting more and more shells. So the atoms are becoming bigger and bigger and bigger, and those valence electrons are going further and further away from the nucleus. So that if they're going further and further away from the nucleus, they're going to be held less tightly. And so you're not going to need very much energy in order to remove the electron. All right, so it's going to be real easy to pluck off electrons, valence electrons, from francium and the other guys down at the very bottom because they're super huge. They're like, they've got so many electrons, they don't even know how to keep track of them all. So they're going to be like, oh, you stole one? Well, I don't care, I got more. Okay, so as you go down a group, the ionization energy is going to decrease as you go down. Because again, you get more and more shells, more and more valence electrons further and further away, easier to pluck them off. All right, so another general rule, smaller atoms are more difficult to ionize because their electrons are held more tightly. Larger atoms, super easy to ionize because their electrons are held less tightly. So ionization energy and atomic size kind of make sense with each other. All right, so let's try a few examples here. You have to pick from the pair which one has the higher ionization energy. So let's start with magnesium versus phosphorus. All right, remember we just said that as you go across, ionization energy increases, right? Because they get closer and closer to those noble gases and want to gain electrons to become like the noble gas. So which one has higher ionization energy? Well, phosphorus does. He's closest to the noble gases. He has to gain electrons rather than lose electrons. Magnesium is also close to the noble gases, but he gets to be like the noble gases by losing electrons. And so ionization energy is the energy to lose an electron. So it's going to be super low. All right, our next one is astatine versus antimony. Okay, right up and down from each other. Okay, so remember, as you go down a group, what happens to size? Size increases. As you increase size, you can't keep track as well of your valence electrons. So which one's going to have higher ionization energy? It's going to be astatine. Okay, antimony is going to be a lot easier to take away electrons than astatine. So astatine is going to have a higher ionization energy. All right, how about nitrogen right there versus silicon, which is here. Okay. All right, so let's think about this. We've got, as you go across, right, ionization energy increases. So it looks like nitrogen will have a greater ionization energy. And remember, as you go down, ionization energy decreases because you get bigger and bigger sizes. So even said, silicon is going to have a lower ionization energy than nitrogen as well, because he's in one group down from, or one row down from nitrogen. So either way you slice it, nitrogen is going to have the higher ionization energy. Okay, the last one we're going to talk about is oxygen, right, which is here, versus chlorine, which is here. And this is another toss-up one, right? Because, if you are comparing going across, then chlorine should be the higher ionization energy since he's closest to the noble gases. But if you go looking, up and down wise, chlorine might be lower in ionization energy, since as you go down, ionization energy decreases. So this one's a toss-up. You can't really tell unless you're given some data. All right, so the last periodic table trend we're going to talk about is what we call metallic character. And metallic character is kind of just, again, as the words describe, it's acting like a metal. If you have metallic character, you're acting like metals. And what do metals do? Metals lose electrons. So, remember that metals are found towards the left-hand side of the periodic table, to the left of the staircase that's right there. And nonmetals are found to the right of that staircase. So, if you look at it and think about it logically, as you move across a period from left to right, metallic character decreases. Because as you go from left to right, you're going to go away from the metals and you're going to hit the nonmetals on this side. All right. However, as you go down a column, okay, metallic character is going to increase. All right, and another way you can think about it is over here, you've got more metals up on the top part than on the bottom part. So you're going to have less and less metals, you're going to have less metals on this side. So, in the nonmetal group, you have less nonmetals on the bottom. So you're going to be increasing metallic character as you go down. Okay, so let's take a look at some examples. All right, so in this one, we're going to choose the one with the most metallic character. So we have tin and we have tellurium here. All right, and remember, as you go across, metallic character is going to decrease because you run into those non-metals, which is not metallic. So the most metallic element would be tin, since he's on the metal side of that staircase, and tellurium's on the other side. Okay, so he's going to be less metal-like. The next one is silicon versus tin. Okay. Again, remember, as you go down, the metallic character is going to increase. So again, between these two, tin is going to be more metallic element than silicon. The third one is bromine here versus tellurium. All right, so if you think about it going left to right, okay, bromine has least metallic character, okay, and then if you think about it, going up and down, metallic character increases. So tellurium has more metallic character. So either way, tellurium is going to have the most metallic character between those two. And like last time, if we did selenium versus iodine, this one's a toss-up because we've got kind of opposite things going on. If we go left to right, iodine would be less metallic, and so selenium would be more metallic. But if you think about it going up and down, iodine would be more metallic and selenium would be less metallic. So that one is a toss-up. Okay, so that wraps up this lecture for Chapter 9 on quantum mechanics and the shell model and periodic table stuff. And so we're going to wrap it up, and we'll see you next time.